There's a piece of wood that's been sitting outside for over 2 decades. No paint, no sealant, no chemical treatment of any kind. It's been through freezing winters, heavy rain, direct summer sun, the full cycle that normally destroys wood piece by piece. And yet when you run your hand across its surface today, there's no rot, no soft spots, no gray weathering. It still looks intact, stable, almost unchanged. Now here's the part that shouldn't make sense. This wasn't protected by adding something to the wood. It was protected by burning it on purpose, and not just lightly. The surface was exposed to fire until it turned black. If you've ever seen wood burn, your instinct is simple. Fire destroys. But in this case, fire did the opposite. It extended the lifespan of that wood, not by a few years, but potentially by 50, 80, even 100 years from a single treatment. So the real question isn't how to do this. We'll get there. The real question is, why does a method this simple, this cheap, and this effective exist? And yet almost nobody uses it, because once you understand that, you're not just learning a technique, you're seeing a system most people never notice. What if fire isn't the enemy of wood, but a tool to redesign it? When wood burns under normal conditions, it's chaotic. Uncontrolled heat, oxygen feeding the flame, structure collapsing into ash. But when you apply fire in a controlled way, something very different happens. The surface doesn't simply burn, it transforms. At a certain temperature range, wood undergoes a process called pyrolysis, where heat breaks down the organic components like cellulose and hemicellulose, releasing gases and leaving behind a carbon-rich layer. This layer is no longer wood in the traditional sense. It's closer to a natural composite, hardened, chemically altered, and fundamentally more stable. And here's the key. This transformation only happens at the surface. Just a few millimeters deep, the outer layer becomes carbonized, while the inner core remains structurally intact, still strong, still load-bearing. You end up with a dual-layer system, a protective shell on the outside, a functional structure on the inside. This is not destruction, it's selective engineering, using energy to reprogram the material itself. And once you see fire this way, you start to realize how powerful that shift really is. So what actually makes this blackened surface so powerful? It's not the burn itself. It's what the burn leaves behind, carbon. When wood is properly charred, the outer layer becomes almost entirely carbon-based, and that changes everything, because carbon behaves very differently from raw wood. First, carbon is biologically inert. Fungi, mold, bacteria, the organisms responsible for rot, rely on organic material they can break down. Carbonized wood offers them nothing. It's like trying to grow on stone. Second, it dramatically reduces moisture penetration. Untreated wood absorbs water, swells, and eventually breaks down from within. But the carbon layer acts like a barrier, slowing water intrusion and stabilizing the material underneath. Third, it resists UV degradation. Sunlight breaks down lignin in natural wood, causing that familiar gray weathered look. Carbon, however, is far less sensitive to UV, meaning the surface stays visually and structurally consistent over time. And finally, insects can't use it as food. No nutrients, no interest. So when you zoom out, this isn't just protection, it's a complete removal of the failure pathways. The wood doesn't fight decay anymore. It simply stops participating in the system that causes it. Long before modern tools, chemicals, or building codes, this method was already optimized. In coastal Japan during the Edo period, carpenters developed a system that didn't rely on precision instruments. It relied on structure. 3 wooden planks were tied together into a triangular column, forming a hollow chimney. The charred surfaces faced inward. A small fire was lit at the base. As heat rose through the column, it created a natural draft, pulling oxygen upward and distributing heat evenly across all 3 interior faces. No gauges, no thermostats, just physics doing the work. Within minutes, the inner surfaces carbonized uniformly from bottom to top. Then the system reset. The planks were separated, cooled, brushed, and sealed. What's remarkable isn't just the result, it's the design logic behind it. This is a self-regulating system. Airflow controls the burn geometry distributes heat. Time is standardized by the structure itself, no external control needed. And that's the deeper insight. The most resilient systems are often the simplest, not because they lack complexity, but because the complexity is embedded into the design. This wasn't just a technique, it was engineering, without industry. At this point, it's tempting to think the method is universal, that you can take any piece of wood, apply fire, and get the same long-term result. But this is where most people go wrong, because the outcome doesn't depend on the fire alone. It depends on the interaction between fire and the material itself. Different wood species behave very differently under heat. Softwoods like cedar or traditional Japanese sugi have low resin content and a consistent grain structure. This allows them to char evenly, forming a stable and uniform carbon layer. Cypress performs similarly well, with strong durability even in humid environments. But move to woods like pine, and the system becomes unstable. High resin content leads to uneven burning, bubbling, and weak spots in the carbon layer. What looks good initially can fail faster over time. Dense hardwoods introduce a different problem. They resist burning, requiring more energy, and that makes the process harder to control, often damaging the structural core before achieving proper surface carbonization. So the real system looks like this: material, heat response, carbon layer quality, longevity. If the first variable is wrong, everything downstream breaks. This isn't just a technique, it's a material-dependent system. Today, this entire system has been compressed into something almost anyone can do in a single afternoon. No traditional chimney setup, no specialized workshop. Just a few simple tools: a propane torch, a wire brush, and a natural oil like linseed or tung. But what matters isn't the tools, it's how energy is applied. You're not trying to burn the wood, you're controlling a narrow window of transformation. Hold the flame a few inches from the surface and move it slowly, evenly. Too fast, and the wood never fully carbonizes, leaving vulnerable gaps. Too slow, and the heat penetrates too deep, damaging the structural core. There's a balance point, where the surface turns from brown to a consistent matte black. That's your signal. The carbon layer has formed. After cooling, brushing removes the fragile soot layer, exposing a more stable texture beneath. Then comes the critical step most people underestimate: oil. The oil doesn't just enhance appearance, it seals the carbon layer, stabilizes it, and extends its lifespan under real-world conditions. Think of the process as a pipeline: energy, transformation, stabilization, sealing. Miss one stage, and the system degrades. Get all four right, and you've created something remarkably durable, with almost no cost. At this point, the obvious question is, if this works so well, why isn't everyone doing it? The answer isn't that the method is hidden, it's that it doesn't fit the way the modern building industry makes money. Most conventional wood protection systems are built around maintenance cycles. Paint degrades, repaint, every few years sealants break down, reapply pressure-treated wood. Eventually replace each step creates ongoing demand for products, labor, and repeat services. But a properly executed charred wood system breaks that cycle. One treatment can last decades. Maintenance is minimal. There's no dependency on proprietary chemicals or brand-specific solutions. From a systems perspective, that creates a mismatch. The homeowner benefits from long-term durability. The industry benefits from recurring intervention. So what gets promoted isn't always what lasts the longest. It's what sustains the economic loop. This doesn't require conspiracy. It's simply how incentives shape visibility. Technologies that reduce maintenance often spread more slowly because they reduce the need for the very systems that would promote them. And that's the pattern, not hidden, just not amplified. Zoom out, and this isn't really a story about wood. It's a story about how knowledge moves and how it gets filtered. The core idea behind this technique has existed for centuries. It didn't require patents, supply chains, or specialized training. It was local knowledge, passed through practice, embedded in communities that needed durable materials with limited resources. Then something changed. As construction became industrialized, materials were standardized, processes were outsourced, and performance was increasingly tied to products, not techniques. Protection became something you buy, not something you understand. And in that shift, certain kinds of knowledge lost visibility, not because they stopped working, but because they didn't integrate into the new system. What we're looking at here is a classic case of knowledge asymmetry: high-value insight, low market amplification, until it gets rediscovered, rebranded, and reintroduced, often at a premium. That's how a method that costs almost nothing in its original form can reappear as a high-end architectural feature with a five-figure price tag. So the real takeaway isn't just how to char wood, it's recognizing the pattern. Sometimes the most powerful systems aren't new, they're just overlooked.